Hey everybody, Kevin C. here, Santa Rosa Junior College Wine Studies Online. We're going to test malic acid by paper chromatography. So today we'll talk a little bit about chromatography basics. So let's get right to it. If we have a wine, say, that has, let's say for example, a wine just has two molecules in it. So we'd have our wine glass here, and we'd have two molecules. Red one smells like passion fruit. Blue one smells like raspberries. That's kind of a strange combination, isn't it? All right, let's say the second one smells like green apples. And as a chemist, I want to analyze those compounds. I want to know how many of each of those compounds are in the wine. And so to analyze them, I've got to separate them. And the way we do that is with chromatography. So the idea of chromatography is you're going to separate a component mixture into its individual molecules. And then you analyze them, you see what's there, and typically how much is there. So in this case, we want to separate the red ones from the blue ones. Well, each molecule has some different properties. Turns out that the red one, that one sticks to Velcro nicely. You didn't know probably these small little molecules have little Velcro hooks attached to them. It's really amazing. All right, so say we have this strip of Velcro. And turns out the blue ones don't stick to Velcro at all. So if we took our wine and we ran it across this Velcro, you know what's going to happen, right? The red ones with the Velcro hooks, they're going to stick to the Velcro. The blue ones, they're going to run right past the Velcro and run right off. Well, we've accomplished some separation. We have the red one stuck here, we have the blue one stuck here. That's basically what happens in chromatography. So you have what is called a mobile phase, and that's what would carry the wine across the Velcro strip. And then you have a stationary phase, and that in this case would be the Velcro strip. And so you separate molecules in a mixture because they have different affinities for the mobile phase relative to the stationary phase. So here our red molecules have great affinity for the Velcro strip, our stationary phase. Turns out the blue ones don't have any affinity for the Velcro phase, the Velcro strip. They just stay in the mobile phase and they get carried right on through. So the mobile phase is moving right on through, and it's carrying stuff that doesn't stick very well. Pretty simple. So what we can do then is we can use this technique in lots of different ways to separate mixtures one from another. And I'll give you a couple at the end, a couple of things, a couple of techniques, chromatography techniques that we're not going to use today. But first we'll talk about the one we are going to use today, which is paper chromatography. So paper chromatography is very simple. You basically take a piece of paper, and I would take a couple of wines, and I would just take a little bit of wine and spot it on the paper. And then I would take a second wine and spot it on the paper a little ways apart from the first spot. And then I'd spot a third wine, and then I'd spot a fourth wine. You can do as many as you want. Just separate the spots one from another. And I let those spots dry. And then I put that piece of paper in a beaker. So let me see if I can draw a beaker here. All right, so put that piece of paper in a beaker. And in the bottom of that beaker, I've got some solvent. So I have a solvent filling up the bottom. And I've got, so this is all solvent down here, and I dip the bottom of that piece of paper in the solvent. And I have the nice all the space around. I have a lid on top of this, so there's a lid on here, and so all the airspace inside of the beaker is saturated with vapor from my solvent. So what happens when I put the paper in the solvent is the solvent actually travels up the paper, right? It has some affinity for the paper, it soaks in, and it gets pulled up the paper because the solvent has the affinity for the paper. And so that becomes our mobile phase. And our paper, that is the stationary phase. Okay, so as the mobile phase travels by my spots of wine down here at the bottom, it pulls those wine spots up. All right, so our wine starts moving up with the mobile phase. That wine is a mixture. And what happens is the molecules in the wine have different affinities for the mobile phase than they do the stationary phase, or molecules have relatively different affinities one for the other, right? So in this case, we're looking at acids. And it turns out that malic acid travels faster in the mobile phase than does tartaric acid. Tartaric acid sticks to the paper better. And so you'll end up getting a separation of tartaric acid from malic acid, and malic acid from lactic acid. So you end up separating your acids one from another. And so it ends up looking like this. So there's your solvent down at the bottom, right? The bottom of the beaker. And in this case, in this example, they put ink instead of wine on the paper. But there's their paper. And as the solvent moves up the paper, it separates the dye into its components, right? So there's some blue and the yellow that make up green, and it gets separated. The solvent front is just how far the solvent has traveled. Here's another example, another diagram that shows it nicely. So again, note that down here at the bottom, here's our origin. That's where we put the spots of wine on the paper. There's the paper. It's all in a tank. It has a lid, etc. And our solvent's down the bottom. So the lab write-up tells you a little bit about the type of solvent. And what happens is our solvent has a dye in it. And that dye turns color at low pH. Well, what would decrease the pH? Acids. So when acids are pulled up and they create some spots on the paper, at each spot, because the pH is lower, because it's an acid, our dye turns color. And so when we dry the paper, our spots turn color, and we can tell where malic, lactic, and tartaric are. And the way we tell is we run some standards. Like, so some of my spots, like this spot here, I might have put in that just tartaric acid. All right, so it's only tartaric. It's a tartaric acid standard. And so when that runs up and stops and forms a nice colored spot once I dry the piece of paper, then I know how far tartaric is going to run given this type of paper and this type of solvent. So if I have a wine solution here, the second spot, if I end up with a spot here, when the wine runs up, I know that's tartaric because it runs the same distance as the tartaric standard. I may have other spots up here, and I can compare those to other standards to see what they are. So the bottom line is you end up with a piece of paper that looks like this. So look across the top here, we've got 6 wines, and the L is lactic. So lactic acid runs faster in this assay. It moves further up. It's closer to the solvent front. The solvent front is just how far the whole solvent has run. So that would be up at the top of the paper. Lactic moves the farthest. Malic moves midway, and tartaric is the slowest. So tartaric sticks to the paper better than to the mobile phase being the solvent that is running up the paper. Well, you can see some of these wines have malic and some don't. And if we're interested in whether a wine has finished malolactic fermentation, you can see wine 6 has plenty of malic, hasn't gone through ML. Wine 5 has no malic. Clearly, it's finished ML. It's got a lot of lactic, which makes sense because the malic has been converted to lactic. There's some lactic in the wine here, but it obviously has not completed ML because it's got a lot of malic still. And that's paper chromatography. Very cool, easy technique, inexpensive, not perfect because you need a decent amount of malic acid to have about 100 milligrams to show up in this assay. So you could have less than 100 milligrams per liter and it wouldn't show up. So it's not perfect. And we'll look at another assay later in the semester, an enzymatic assay, which is more sensitive for malic. There are a couple other ways of doing chromatography. Gas chromatography we use a lot in wine analysis. And we use gas chromatography mass spectrometry, which you don't have to worry too much about right now, but just so you know the acronym GCMS, this is a GCMS machine. And the principle is really similar to paper chromatography. Here's a diagram of how it works. This is the GC over here on the left in the diagram, and this is the mass spectrometer or mass spec over on the right. We're not going to talk about how the mass spec works, but I want to tell you a little bit about how the GC works. And you simply have a long column, which is this coil here, and all that is a long glass tube, very narrow, and inside the tube there's a coating, and the coating is the stationary phase. So there's a coating inside the tube, and the coating is the stationary phase. And so if you inject, over here there's an injector, you can inject a wine sample in there, and the different components in the wine will separate because different components stick to the coating differently. In this case, our carrier, our mobile phase, is a carrier gas. Usually we use just helium. He, the chemical symbol, use helium in a wine analysis. But the helium carries all the wine through. You vaporize the wine, so it's just gas. You heat it up. The helium carries it through, and based on the relative affinity of different molecules for that coating inside this long glass column, it separates all these molecules. And then the mass spectrometer is what tells you what the molecule is. So the molecules come out of the gas chromatograph one at a time because they've been separated. And then the mass spectrometer tells you what they are as they come out. In our case, we're using paper to do the separation. We're using dye to tell us that something is there, and we're comparing to a standard to identify what that something is, what that acid is. So that's how it works. Thanks for listening, and we'll see you next time.